Hi dear students, today let's discuss about the magnetic effect of electric current part 4, that is electromagnetic induction and working of a generator. Okay, let's start. Dear students, we have studied that when a current carrying conductor is placed in a magnetic field such that the direction of current is perpendicular to the magnetic field and it experiences a force, right? And this is nothing but Fleming's left hand rule. And this force causes the conductor to move. Now let us imagine a situation in which a conductor is moving inside a magnetic field or a magnetic field is changing around a fixed conductor. What will happen? This was first studied by English physicist Michael Faraday. In 1831, Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric current. To observe this, let's perform a small activity. So, observe this activity carefully. Okay, here take a coil of wire having large number of turns, and this acts as a solenoid. Okay, and connect the ends of the coil to a galvanometer as shown here. So what is galvanometer? It is a device like ammeter, but it only detects the presence of current in the circuit. Okay, see, ammeter is a device that measures the current, right? That measures the current in the circuit, whereas galvanometer detects the presence of current in the circuit. Okay, and take a bar magnet and move its north pole towards the end of the coil. Do you find any change in the galvanometer needle? Observe the pointer of galvanometer. So what do you see? Yes, you see the deflection, right? So there is a momentary deflection in the needle of the galvanometer, say to the right, and this indicates the presence of current in the coil, and the deflection becomes zero the moment the motion of the magnet stops, as you can see here. Now withdraw the north pole of the magnet away from the coil. Now the galvanometer is deflected towards the left, showing that the current is now set up in the direction opposite to the first, right? Yes. So as you take away the bar magnet from the coil, again it comes to rest. Now, when you place a bar magnet stationary at a point near to the coil, keeping north pole towards the end of the coil, then we see that galvanometer needle deflects towards the right when the coil is moved towards the north pole of the magnet. Similarly, the needle moves towards left when the coil is moved away. And when the coil is kept stationary with respect to the magnet, then the deflection of the galvanometer drops to zero. So what do you conclude from this activity? When the coil and magnet are both stationary, then there is no deflection in the galvanometer. It is thus clear from this activity that motion of the magnet with respect to the coil produces an induced potential difference. Okay, there should be a relative motion between coil as well as a magnet. Then they creates potential difference, and due to this potential difference, it it induces electric current in the circuit. and this phenomenon is called as electromagnetic induction. Okay, so what is electromagnetic induction? The process by which electric current is produced. When the electric current is produced, when there is a change in magnetic field associated with the conductor, and this is called electromagnetic induction. Okay, let's perform one more activity to make the concept clear. Okay, here instead of bar magnet, we have taken two coils. Okay, two coils. Let me explain about that. Take two different coils of copper wire having large number of turns. Okay, here coil 1 have large number of turns and coil 2 has less number of turns, and it is called secondary coil. So what is primary coil? Primary coil is a coil 1 having large number of turns, and that behave like a magnet. Then coil 2, that is secondary coil, it is connected to the galvanometer, and the first coil is connected to the battery. Okay, here coil 1 is a connected series with the battery and a plug key, and coil 2 is connected to a galvanometer. Okay, now plug in the key, observe the galvanometer. Observe the galvanometer. Yes, you see deflection, right? Yes, you'll observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to zero. I'll repeat it. Observe it now again. Observe the reading of galvanometer. That pointer, it jumps to one side and suddenly it returns to zero. So it indicates that the momentary current in coil 2. Understood? So now again disconnect coil 1 from battery. You'll observe that the needle momentarily moves, but to the opposite side. So it means that now the current flows in opposite direction. Okay, so in this activity we observe that as soon as the current in coil 1 reaches either a steady value or zero, the galvanometer in coil 2 shows no deflection. From these two observations, we can conclude that the potential difference is induced in the coil 2 whenever the electric current through the coil 1 is changing. Here the coil 1 is called primary coil having large number of turns, and coil 2 is called secondary coil. Okay, as the current in the first coil changes, the magnetic field associated with it also changes. Okay, that coil 1 acts as a magnet here. Thus, the magnetic field lines around the secondary coil also change. Hence, the change in magnetic field lines associated with secondary coil is cause of induced electric current in it. So, this process by which a changing magnetic field in a conductor induces current in another conductor is called electromagnetic induction. I repeat, the process by which a changing magnetic field in a conductor induces current in another conductor. This is also called as electromotive force. So in practice, we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. Okay, and it is convenient in most situations to move the coil in a magnetic field. The induced current is found to be highest when the direction of motion of the coil is at right angles to the magnetic field. Okay, in this situation we can use a simple rule to know the direction of the induced current is Fleming's right hand rule. Earlier we learned the Fleming's left hand rule, right? Here electromagnetic induction, it is also called as a Fleming's right hand rule. So what does it say? Okay, stretch the thumb, forefinger and middle finger of right hand so that they are perpendicular to each other as shown in the figure. If the forefinger indicates the direction of the magnetic field and thumb shows the direction of motion of conductor, then the middle finger will shows the direction of induced current. So what is the difference in Fleming's right hand rule and left hand rule? So in left hand rule, first comes forefinger, right? Forefinger indicates the direction of the magnetic field, then the middle finger indicates the direction of the current, and then thumb shows the direction of the motion of the conductor. Here, first forefinger only, forefinger indicates the direction of the magnetic field, then thumb comes, okay? Thumb shows the direction of the conductor, and finally the middle finger shows the direction of the induced current. Okay, that is the difference, main difference. Understand that. This simple rule is called Fleming's right hand rule. Some devices work by using this principle only. Okay, that is electromagnetic induction or Fleming's right hand rule. That is, one of the device is electric generator. Now let us see the working of electric generator. So observe this video to understand about the working of electric generator.
How do power stations provide electricity to thousands of houses around a city? They don't use giant batteries. They do that by spinning a giant turbine like this. And to spin such a turbine, some power stations use very hot steam that blows over the turbines and spins it. Or maybe we can use the energy of the falling water. Or another example could be we fit these inside giant windmills and let the wind do the work for us. Whichever way you choose, all we do is spin a giant turbine. But how does turning something create electricity? Well, the technology is based on electromagnetic induction, discovered by Michael Faraday more than 200 years ago. The basic idea is that if you take a wire and move it up or down inside a magnetic field, it induces an electric current. So all we have to do is attach a coil of wire to these giant turbines and place them inside a magnetic field. As the turbine rotates, the coil starts rotating and the wires start moving up and down inside the magnetic field. That produces the electric current. And this can now be used to light up things. These devices are called electric generators. They convert spinning or mechanical energy into electrical energy. So let's look at them in detail now. So let's start by figuring out in what direction a current gets induced or generated in this coil once it starts rotating. So let's say, in our example, the coil rotates clockwise, somewhat like this. Now, how do we figure out the direction of the induced current? Well, we have already learned something called the Fleming's right-hand generator rule, which says you stretch the fingers of your right hand like this, such that they are perpendicular to each other. Then the thumb represents the direction of the motion of the wire, that is, the direction in which you're pushing the wire. The forefinger gives us the direction of the magnetic field. Then our middle finger will give us the direction of the current. So all we have to do is align our right hand to make sure the thumb and the forefinger point in the direction of the motion and the magnetic field. Then the middle finger will give us the direction of the current. So let's use our right hand rule on the pink wire that is going upwards, as you can see, and on the blue wire that is moving downwards. So it'll be a great idea if you can first see whether you can try it yourself. So go ahead and use your right hand and see if you can figure out the direction of the current in the pink and the blue wire. Alright, if you've done it, let's first start with the pink wire. Because the pink wire is going up, the thumb should be pointing upwards. The magnetic field is to the right, so the forefinger should be pointing to the right. And so if we align our fingers that way, it will look like this. Since the middle finger is pointing inwards, this means the current in the pink wire must be inwards. Similarly, for the blue wire is moving downwards. So the thumb will be pointing down, the forefinger will still be pointing to the right. And so if we arrange our right hand over here, it will look like this. The middle finger is pointing out of the screen. That means the current in the blue wire will be coming out of the screen. So what we have seen is if a wire is moving upwards over here, then the current will be into the screen. And if the wire is moving downwards, then the current will be out of the screen. Remember this will be important. So now let's get rid of the hands and put arrow marks to indicate the current. And now we can guess what direction the current will be in the rest of the wires. Since the current has to flow from the pink to the blue, we can say that the current has to move here like this. And then the current has to move here this way. It goes out. It goes to that external circuit, maybe where there is a bulb. We'll look at that later. Then the current comes back like this and it flows in this way. And the current continues to flow like this as the coil keeps rotating. Because you can see the pink wire is still going up and the blue wire is still going down. Until we come to this point. Because now the pink wire starts moving downwards. And now the blue wire starts moving upwards. Can you see that? Again, if I go back and come back again, notice the pink wire is coming down and the blue wire is going up. This means now the current in the pink wire should be out of the screen, because we already saw using our right hand rule. When the wire is going down, the current must be out. And in the blue wire, which is going up, the current must now be inwards. In other words, the current will now change its direction. This is the important thing. So the current changes its direction and it continues to flow this way until again the pink wire comes on the left side. Because now again the pink wire starts going up, the blue wire starts going down, and as a result the current in the pink wire will be inwards, the current in the blue wire will now be outwards, the current will again reverse. So every time our coil is in this position, which is perpendicular to the magnetic field, we will see that the current direction will flip. And so if you look at the entire animation now, it looks somewhat like this. Every time the coil comes in this position, perpendicular to the magnetic field, the current direction keeps changing. Now, of course, in the animation, I'm pausing the animation when my coil is perpendicular to the magnetic field so that we can see the current flipping its direction. But of course, in reality, the coil will be pushed continuously. There will be no stopping. There will be no jerking motion like we are seeing over here. Now, the next question we might have is, how do we connect this coil to an external circuit, like say to a bulb? Well, we could connect it directly, right? Well, let's see what happens if we connect the circuit directly. Current will flow, no problem. But as the coil starts rotating, notice the wires start twisting and tangling and turning and whatnot. So that's going to be a problem. So to avoid that, we will not connect the wires directly. Instead, we will use an arrangement involving brushes and slip rings. It looks somewhat like this. So basically we have two metallic rings, the pink one and a blue one. And what you may not make out from my diagram over here is that each ring is connected to one wire only. So the pink ring is only connected to the left wire and the blue ring is only connected to the right wire. And these wires are connected to carbon brushes, which is also conducting, and they are just touching these rings so that there is a metallic contact, but they're not stuck to it. So right now there is a contact, the circuit is complete, and as a result the current comes out of the blue ring, as you can see, moves this way, and current flows into the pink ring and goes like this. And when the coil starts rotating, as you can see, the rings rotate along with the coil. But since the brushes are not stuck to the rings just slip through the brushes. That's why they're called as slip rings. As a result, the brushes will not rotate. That solves the problem of wires twisting and tangling. And all the while, an electric contact is maintained. Now, once our coil comes in this position, we have seen that the current reverses. So now the current will flow out of the pink ring, goes like this through the bulb, and now enters into the blue ring. So for every half a rotation, the current through the bulb also reverses. Let's say when the current is flowing this way, the bulb glows blue. And let's say when the current reverses and flows like this, the bulb will glow yellow. And so now if you look at the entire animation, it looks somewhat like this. And so we have successfully built our generator. And what's interesting to see is that the current from that generator is continuously changing its direction. Such a current is called alternating current, or AC. And this might sound a little weird, but it turns out that when you want to transmit electricity over a long distance, like from the power station to your houses, then alternating currents, or AC, have some great advantages over unidirectional currents, or DC. And it's for that reason the current that we get at our houses, the electricity that we get at our houses, are all AC. And these generators are called AC generators. Finally, what if we want to build a DC generator where we don't want the current direction to change? We want it to remain the same throughout. Let's say in this direction. How do we do that? Well, to build that, first let's get rid of these rings. Alright, now to make sure that the current direction remains the same, what we will need is that these brushes to continuously keep changing contacts between these wires for every half a rotation. Let's see why. So if I want the current to flow this way, right now in this position, I can connect this brush to this wire, so the pink side, so that the current flows like this and comes out. But as the coil rotates, notice once it comes to this position, we have seen that the current starts flipping, current reverses. And so now, to maintain the current in the same direction, we would now require this brush to come in contact with this wire. That is the blue side, right? And then again, once we come to this position, again it flips, the current flips, and again we would want now this brush to come in contact with this side. And so as a result, can you see that for every half a rotation, we would want the contacts to keep changing. But how do we make sure that happens automatically? We can do that by attaching split rings. Split rings, as the name suggests, is a ring that is split in between, giving two half rings with some gap in between. Now let's see how this arrangement automatically changes contact for every half a rotation. So right now, this brush is in contact with the pink side. But as the coil rotates and comes to this position, the current reverses, and now notice the brush is in contact with the blue side, making sure the current still flows in the same direction through the bulb. Again, as the coil comes to now this position, finishing another half a rotation, again notice it just changed contact. It is now in contact with the pink ring, connected to the pink side. And this way, we have now built our DC generator, where the current only flows in one direction through any external circuit. And this arrangement, which helps us automatically change contacts, we call them as commutators. So split rings act like commutators. So to summarize what we learned, if you take a coil and spin in a magnetic field, then due to electromagnetic induction, a current gets generated in that coil. Now the direction of the current depends on whether the wire is going up or whether it's going down. And as a result, for every half a rotation, we see that the direction of the current keeps changing. And so this generator is called an AC generator because it generates an alternating current, a current whose direction keeps continuously changing. On the other hand, if we use split rings, then it acts like a commutator. It keeps changing the contacts for every half a rotation and makes sure that the current does not change the direction in the external circuit. We call this a DC generator. And so this is how we can generate electricity just by rotating a coil in between a couple of magnets.
So I hope this is understood. Now let's recall once again about the working of electric generator. Okay, so what is electric generator? It is also called as dynamo. Generator is a device, it is used to convert mechanical energy into electrical energy. So motor converts electrical energy into mechanical energy, whereas dynamo, it converts mechanical energy into electrical energy. And the principle of electric generator is based on electromagnetic induction. Okay, now let's see the construction of a AC generator, that is alternating current generator. So it consists of an insulated copper coil of many turns wound over a soft iron core. Here ABCD is a armature. It is also called as armature. This rectangular coil is also called as armature. Then this coil is placed between the poles of piece of concave cylindrical magnet like a motor. Then the free ends of the copper wire are connected to two rings R1 and R2 of copper. Here instead of split rings, slip rings are used. Okay, in motor split rings are used. Here slip rings are used. And then two carbon brushes attach the rings. The brushes are then connected to the battery. Now let's see the working of AC generator. When the coil is made to rotate in clockwise direction, the magnetic field linked with coil changes, and this induces an electric current in the coil ABCD. Here one more thing is that battery is not connected. Okay, here the electric sources are connected like bulb, but in motor battery is connected. That means when we pass current to the coil, it creates a magnetic field and it starts to rotate. But here the difference is we are rotating the coil, then it generates current, electricity, and we can detect that through the glowing of a bulb. During the first half of the rotation, the current flows along ABCD through that direction, then R1, B1 and then B2. Then during the second half of the rotation, current is induced in the coil along DCBA. Through that direction, the current moves, and from R2 to B2 to then D1. Okay, so what is alternating current? If the current changes its direction after equal intervals of time, it is called a alternating current. So how do we represent it? Through the graph. This is the graphical representation of alternating current that changes its direction after equal intervals of time. But direct current, the direction in direct current, direction do not change with the time. Okay, in the graph you can see the straight line parallel to the time. That means here the direction will not change. Okay, that is the main difference between AC and DC. So let's see what is the difference between AC generator and DC generator. So in AC generator, the two ends of the coil are connected to full rings of copper, and in DC generator, two ends of the coils are connected to commutator consisting of two half rings of copper. That means two split rings are used. Then the second difference is the direction of the current produced changes every half revolution, whereas in DC generator the direction of current produced is same in both the revolution. Okay, now what is the difference between generator and motor? Yes, generator converts mechanical energy into electrical energy, motor converts electrical energy into mechanical energy. And then the second one is the coil is rotated in an electric field by an external force, and that is through the battery, and it induces an electric current of the coil of the motor, whereas in the motor current is applied to the coil resulting in rotation of the coil of the motor, but in generator external force, mechanical force is applied so that it induces the electric current in the coil. Okay, and why is alternating current considered to be advantageous over direct current for long range transmission of electrical energy? Because alternating voltage can be stepped up or stepped down by using transformers. Transformer is a device, you might have seen that it regulates the voltage. Okay, and this makes AC more suitable than DC for transmission of electrical power over long distance without much loss of energy. Okay, so this is about the working of electric generator and electromagnetic induction. Now let's discuss about the question answers related to this topic now. So the first one, explain different ways to induce current in a coil. The answer is moving magnet towards or away from the coil or vice versa, and changing current in the neighboring coil. In these two ways we can induce current in a coil. That is, in the first activity we saw that movement of the magnet, right? And then second case we saw that changing current in the primary coil, that induces current in the secondary coil. These are the two ways to induce current in the coil. Next one, state the principle of an electric generator. So it works based on the principle of electromagnetic induction. When a rectangular coil is rotated in uniform magnetic field, an induced voltage is generated between the ends of the coil. Name some sources of direct current. DC sources are cell, battery and DC generator. Then which source produces alternating current? AC generator and inverters, they produces alternating current. Choose the correct option. A rectangular coil of copper wire is rotated in magnetic field. The direction of the induced current changes once in each half revolution. Okay, why? Because when a rectangular coil of copper is rotated in a magnetic field, the direction of the induced current changes once in each half rotation. Then this is exercise part, question answers. In that first one, which of the following correctly describes the magnetic field near a long straight wire? So the answer is option D. The field consists of concentric circles. Magnetic field lines, these represents centered on the wire. Okay, option D is the right answer. Then the phenomenon of electromagnetic induction is the right answer is C. Producing induced current in a coil due to relative motion between magnet and the coil. Third one, the device used for producing electric current is option A. Generator is the right answer. Okay, galvanometer detects the presence of current. Ammeter measures the current. Motor converts converts electrical energy into mechanical energy. Okay, and which device is used for producing electric current? That is generator. Then the essential difference between an AC generator and DC generator is option D, that is AC generator has a slip rings while the DC generator has a commutator, that is split rings. Okay, so please copy these question answers to your notes and learn these question answers. Thank you.